Hello everyone. Welcome to Global Institute of Innovation and Entrepreneurship. I am Nilanjana Chaudhary. I hold my doctorate degree from Indian Institute of Technology, Kharagpur, and I have done my postdoctorate from University of Michigan, USA, as well as from Technion Israel Institute of Technology, Israel. Today I discuss about the quantum mechanical model for structure of atom. So according to quantum mechanical model, the location of electron in an atom is uncertain and it can be described by the probability of finding it in a certain position. So here comes the concept of orbital. So what is orbital? Orbital is a three-dimensional region around the nucleus where the probability of finding the electron is maximum, that is 90% of time the electron is located on that particular position. So the probable location of an electron around the nucleus can be defined by solving Schrodinger's equation using four quantum numbers, and these are principal quantum number, azimuthal quantum number, magnetic quantum number and spin quantum number. So first we will discuss about the principal quantum number. Principal quantum number was given by scientist Niels Bohr. It is denoted by small n and the value of n is any positive integer, that is 1, 2, 3, 4, 5, 6, 7 up to infinity. So the principal quantum number represents the energy level of cell. It determines size as well as energy of the orbital. If you look at the diagram, the n equal to 1 energy level represent K cell, n equal to 2 energy level represent L cell, n equal to 3 energy level represent M cell, and n equal to 4 represent N cell. And as the value of n increases, the size of the atom increases as well as the energy of the electron also increases with the increased value of n. Principal quantum number gives us idea about the radius, energy of the electron, potential energy of the electron, as also speed of electron in nth level. So the radius Rn is given by 0.529 into n square by j. For hydrogen atom, j equal to 1, and for n equal to 1, the first Bohr radius is 0.529 angstrom. Whereas the energy of the electron in nth level equal to n equal to minus k z square by n square. When n equal to 1 and z equal to 1, so the energy of the electron in first energy level equal to minus 13.6 eV, that is equal to 2.18 into 10 to the power minus 18 joule. The potential energy, that is EP, given by minus 2 kz square by n square, and the speed of the electron in nth level is given by 2.18 into 10 to the power 6 checked by n meter per second. We can also calculate the maximum number of electrons by the 2n square formula. So when n equal to 1, K cell has 2 electrons. For n equal to 2, L has 8 electrons. For n equal to 3, M has 18 electrons. And for n equal to 4, N has 32 electrons. Total number of orbitals in n cell is also given by n square. So for n equal to 1, K has 1 orbital. For n equal to 2, L has 4 orbitals. For n equal to 3, N has 9 orbitals. And for n equal to 4, N has 16 orbitals. So if we know the value of n, we can calculate the maximum number of electrons as well as total number of orbitals in an energy level. Bohr model. Given the Bohr model was successful to explain the spectra for hydrogen atom as well as hydrogen atom-like species. So, when energy is supplied, the electron in the ground state absorbs the energy and goes to the higher excited state. And this phenomena is known as absorption, and the spectra contains the spectral lines due to the transition from ground state to excited state. Whereas in case of emission, the electron from excited state come back to the ground state and release the energy. And the spectrum contains the spectral lines due to the electronic transition from excited state to the ground state. So Bohr model shows that the hydrogen atom spectrum contains one single line. But when the spectra was recorded under high resolution spectrograph, we can see two lines. But Bohr was unsuccessful to explain the fine spectra of hydrogen atom as well as the spectra for the multi-electron system. And here, to explain the fine spectrum of hydrogen atom, another quantum number was introduced, and that is known as azimuthal quantum number and is given by small l. And for a given value of n, the possible values of l are 0 to n minus 1. So when n equal to 1, the possible values of l equal to 0, indicating a subset. For n equal to 2, the possible value of L are 0 and 1 indicates a P subset. For n equal to 3, the possible values of L are 0, 1 and 2 subset indicating SPG subcell. So here we can see that the first energy level has only one sub-energy level. For second energy level has two sub-energy level, and for third energy level has three sub-energy level. So the value of L is dependent on the principal quantum number. That's why the azimuthal quantum number is also known as subsidiary quantum number. So the azimuthal quantum number gives us the idea about the subcell. We can also calculate the number of orbitals in a subcell, that is given by 2L plus 1. So when L equal to 0, a subcell has 1 orbital. For L equal to 1, a subcell has 3 orbitals. When L equal to 2, this subcell has 5 orbitals, and for L equal to 3, F has 7 orbitals, and L equal to 4, G has 9 orbitals. We can also calculate the orbital angular momentum, and that is given by root over L into L plus 1 into h by 2 pi. So if we know the value of L, we can calculate the orbital angular momentum of electron. The azimuthal quantum number gives us the shape of the orbital. So for S orbital has the spherical shape, for E orbital has dumbbell shape, D has double shape, and F has more complex shape. So we can also explain the fine spectra of hydrogen atom by using the azimuthal quantum number. So for n equal to 2, there is 2s and 2p sub-energy level. So for the emission, the electron can exist either 2s or 2p sub-energy level, and the electron can come back to the n equal to 1 energy level from 2s or 2p sub-energy level, giving two transitions which correspond to spectral lines. And as the energy difference between 2s and 2p is very small, that's why the two spectral lines are closely spaced. So the azimuthal quantum number was successful to explain the fine spectra of hydrogen atom. The third quantum number is magnetic quantum number. The magnetic quantum number is introduced to explain the spectral splitting in presence of magnetic field, which is known as Zeeman effect. And if we look at the diagram, we can see that without magnetic field, there is only one spectral line in the spectrum. This is because due to the single transition of electron from 1s to 2p orbital. But in presence of magnetic field, the spectrum contains more spectral lines. This is because the 2p subcell gives 3 different energy levels, which explain the 3 different transitions from ground state to excited state, which gives 3 more three spectral lines into the spectrum. The magnetic quantum number was denoted by small m, and the value of n is minus L to plus L, including 0. So when L equal to 0, value of n is 0. So s orbital has only one orientation. For L equal to 1, the value of m are minus 1, 0 and plus 1. So p orbital has three different orientation. For L equal to 2, d orbital has 5 different n values, which gives 5 different orientation of d orbitals, and for L equal to 3 orbitals, so F has 7 different orientation. So if we look at the p orbitals, we can see that when the p orbitals are oriented along x-axis, it is known as px orbital. When they are oriented along y-axis, known as py orbital, and when they are oriented along z-axis, known as pz orbital. And the magnetic quantum number for pz orbital is 0. Whereas for d orbitals, for xy orbital, the orbital lies between x and y-axis. For dyz orbital, the orbital lies between y and z axis, and for the xz orbital lies between x and z axis. Whereas in case of dx square minus y square orbital, the orbital lies on the x and y axis, and for dz square orbital, the orbital lies on the z axis. And by convention, the magnetic quantum number for dz square orbital is 0. So magnetic quantum number gives us idea about the three-dimensional orientation of orbital, as well as it is able to explain the fine spectra in presence of magnetic field. The fourth quantum number is given by the spin quantum number, and it is denoted by small s. So we know that the electron is revolving around the nucleus, and at the same time it is also spinning around its own axis. It refers to orientation of spin of electron. One is clockwise and another is anti-clockwise. The clockwise rotation is given by spin up arrow, and the anti-clockwise rotation is given by spin down arrow. And the clockwise rotation is given by the spin value is plus up for clockwise rotation, and for anti-clockwise rotation the spin value is minus up, and they represent two opposite direction of spinning of electron. We can also calculate the spin angular momentum, and it is given by root over s into s plus 1 into h by 2 pi, and also total spin of the electron in the atom is equal to n by 2, where n equal to number of unpaired electrons. So in a nutshell, we can tell that the first three electron gives us the idea about the location of electron, and the third one gives us the idea about the spin of the electron. So we have discussed about the theory. Now we can discuss some numerical problems, and the first is about the correct set of 4 quantum numbers for the valence electron of rubidium atom. So the electronic configuration for rubidium atom is krypton 5s1, and the valence electron is existed on the 5s orbital. So for the 5s orbital, the value of n equal to the principal quantum number is n equal to 5. So for s orbital, the azimuthal quantum number, that is L equal to 0. The corresponding magnetic quantum number is 0, and the possible spin values are plus half or minus half. The second one is about the orbital angular momentum of d electron, and we know the orbital angular momentum is given by root over L into L plus 1 into h by 2 pi. So for d electron, the azimuthal quantum number L equal to 2. So if we put the value of L in the equation of root over L into L plus 1 into h by 2 pi, we will give the value of root 6 into h by 2 pi. The third one is about the 4 quantum numbers for the 19th electron in chromium atom, and here the electronic configuration is 1s2, 2s2, 3p6, 3s2, 3p6, 4s1 and 3d5. So the valence the 19th electron is in the 4s orbital. So for 4s orbital, the principal quantum number is 4. For s orbital, azimuthal quantum number is 0. So for L equal to 0, the corresponding n equal to 0, and the possible swing values are plus up or minus up. Thank you.